Francisco, and I thank also the organizers for inviting me to give a talk, and I'm particularly honored to be able to talk in this Ellie Memorial session. I thank you also to share with me a thought on Ellie, on her intelligence and her knowledge and her generosity and enthusiasm for science. I want to shift you now to my subject. I'm a chemist, I'm a photochemist, and I like to think of photons coming in and out of molecules and triggering reactions by light. So this is the subject overall that I will like to share with you, and my work is driven by that. I want to talk to you today of nanoparticle-molecule interactions and why do I address this subject. Well, on one side is that I will try to convince you that nanoparticles can help improve detection of low-emitting fluorophores, and this will open the window for detecting intrinsic fluorescence, perhaps, of molecules and not marking, perhaps. The other part is that I will show you that nanoparticles can reduce the importance of photobleaching or can make you take advantage of the existence of photobleaching, which you can never prevent when you are using light and molecules. The questions to be addressed when you think about designing a nanoparticle and molecule hybrid for sensing is, well, you can choose at which distance you can place the molecule from the nanoparticle, which nanoparticle diameter can you use or size, and which are the spectral features of the fluorophore that are most adequate to build a sensor. And then when you try to do the experiment, then what would be the best situation, for example, for brightness contrast or for long monitoring times? Then another question which can interest a photochemist, and I will try to show you that it can be useful, is the question if we can influence other pathways that are not only absorption and fluorescence, for example, isomerization pathways, through the presence of the nanoparticle. The outline of the talk then will be, I'll give you a brief introduction of the properties of the nanoparticle that are relevant for these studies. For example, what is called the plasmonic band. What is the interaction of these nanoparticles with the electronic states of molecules, and what are the consequences for photochemistry and photophysics. And then I'll show you experiments on increased sensitivity and detection and prolonged time traces. And then I will shift you to probes that are used for super resolution and try to see what happens when photoisomerization pathway that is essential for some techniques in super resolution can be influenced by the presence of a nanoparticle and how it can be coupled to fluorescence switching. So magnetic nanoparticles are interesting entities for fluorescence because they have moving electrons, and moving electrons originate what is called the plasmonic band, which has to do with a typical resonance effect of electrons in the structure that can come into resonance with the electric field. There is a characteristic frequency for each structure which depends on the material and on the shape and on the size that gives a special enhancement of the electric field, and this means essentially locally more light, and this more light is quite confined in space in regions which are comparable to the size of the nanoparticle. So the effects on the photophysics of the probe is that you can have an increased excitation rate. This means the molecule can absorb more photons per unit time. And it also increases the emission rate. These two facts have consequences in the brightness of the molecule, the brightness you observe when you shine light on the probe. There is also an excitation quenching. This means the molecule does not emit. It transfers the electronic energy to the nanoparticle, and this is transformed into heat. But I will show you that you can even take advantage of this effect. These three effects are distance dependent. So depending on which of them is more important as a function of the distance, you can have an emission quenching of a molecule. This means that the molecule will not emit light at very short distances from a nanostructure, from a metallic nanostructure. Then, as you go further away, you see an emission enhancement at intermediate distance in the nanometer size scale. And of course, at long distances, where the influence of the nanoparticle is decaying, you see no change. Here I show you the relevant photophysical pathways. You have a ground state, an excited state of the isolated molecule on top, and you have an excitation rate which brings you the molecule from the ground state to the excited state, which is called here S1. And from there, the molecule can either emit light in a radiative process, can deactivate in a non-radiative process, or sometimes it can photobleach. Photobleach means that the molecule just permanently loses its ability to absorb or emit any of them. The zero superscript processes are the processes within the isolated molecules, and when you connect the molecule to a nanoparticle, the interaction with the electrons of this structure makes changes in the excitation rate, the radiative rate, Kr, and it adds a new pathway, which is an energy transfer from the molecule, the excited state S1, to the nanoparticle. This modifies the photophysics and the rate of many processes. In particularly, it changes the emission quantum yield. This is the number of fluorescent emitted photons per absorbed photons, which is given here the name of phi. Phi 0 is in the isolated molecules and phi is in the molecule. Well, it's not important the expression really, but the mathematical expression, but it is important that you notice that through the change of the rate of these processes, the efficiency of emission is changed. These plots here show calculations for a gold nanoparticle of 40 nanometers irradiated at 540 nanometers and a molecule of quantum efficiency of 1. The plot on the upper left shows you the excitation enhancement. At very low distances from the nanoparticle, the molecule can absorb much more photons. So this brings an increase in the brightness. The emission quantum yield cannot have a higher efficiency because it already has an efficiency of 1. But as a consequence of the two processes, the brightness is a result of absorption enhancement and of emission enhancement. You don't have emission enhancement, but you have absorption enhancement. And the plot in the low part of the screen shows you the gain in brightness, GB, as a function of the distance from the molecule to the nanoparticle. The gain in brightness is compared to the isolated molecule. So you have a factor of 2 at distances of about 20 nanometers. This means the molecule is twice as bright as it could be when it is isolated. Well, now this increase in the brightness depends on the efficiency of the molecule. And the less efficient the molecule is when it is isolated to emit light, the higher the enhancement is. And this is quite reasonable to understand. You have possibilities to enhance molecules that do other things other than fluoresce, in that you increase the emission rate. So, for example, for molecules of 1% fluorescence emission when isolated, the green curve, you can have an enhancement of 70 at about 10 nanometers from the nanostructure. In all, GB which is the gain in brightness, is approximately inversely proportional to the emission quantum yield of the molecule. And another not so important now consequence is that the location of the increased region, which is the sharp region down the curves, is shifted nearer to the nanoparticle when the emission quantum yield is lower for the molecule. Now, you can ask which would be the size of the nanoparticle to use. Well, the bigger the nanoparticle, the greater the enhancement. These plots show you in black the maximum gain in brightness to the left. See, for molecules of two different emission quantum yields, 10%, 0.1, and 1%, 0.01 in the lower part. This is in black, and in red is the position of the maximum, of the peak, which I showed you in these curves. So I'm showing you the absolute value of the peak and the position of the peak here in these plots. And the message of these plots is that they are different for the different efficiencies. But for example, for molecules of 1% emission, enhancement begins with particles of 6 nanometers. Smaller nanoparticles hardly give any change in the brightness of the molecule. Whereas if you go to 10% emitting molecules, the nanoparticles have to be at least 15 nanometer radius. So small nanoparticles are not that efficient. And we don't want to go to very, very big nanoparticles, because then you are like loading the molecule with a really big structure. The other important factor for imaging, for example, is the number of photons you can get out of a molecule before it photobleaches. And this has only to do with the rate of the radiative rate constant to the probability of bleaching. And if you compare the molecule bound to the nanoparticle or interacting with the nanoparticle to the isolated molecule, then you obtain a gain in photon which only depends on the increase in the radiative rate. I'm not going to show you calculations on the wavelength dependence, but the conclusion of this is that the gain in brightness and the gain in photons can have maximum at different wavelengths of the absorption of the molecule. So you can tune the absorption of the molecule to have a better performance in brightness or a better performance in the number of photons. As a summary of all the calculations that you can do and the design variables, the performance of the sensing will depend on, in a nanoparticle molecule hybrid, on the molecular emission quantum yield, on the nanoparticle molecule distance, on the orientation, because absorption and emission are orientation-dependent processes, on the nanoparticle radius and geometry in all, and on the molecular absorption and emission wavelength. So you have a multidimensional space to design your hybrid. I'm going to show you now experiments that we designed to see this and to see the performance of this and to quantitatively measure what is the performance you are expected to obtain. I will show you one experiment on detection on an enhanced contrast compared to the background, where the molecules in the vicinity of a nanoparticle can be detected with respect to background where no nanoparticle exists, to prolonged monitoring times, and a brightness enhancement through photoisomerization. The first one is an experiment we performed with nanoparticles placed on a glass plate. These nanoparticles are made of gold, and they have a silicon layer that works as spacers for the molecules. The 10 micrographies are shown here. You have nanoparticles of 13 nanometers with 8, 18, and 14 nanometers silicon shell, and we use as a blank experiment silicon nanoparticles without the gold core. The plot to the right shows you the extinction spectrum of single nanoparticles, which we use as criterion to see that we are really measuring on a nanoparticle. The contrast experiment is given here, and you see that in the lower part you see transmission micrographs where you can locate the nanoparticles, and on the upper graphs you have the same region but monitored by fluorescence. And you clearly see that, for example, for rose bengal, a fluorophore that has 2% fluorescence quantum yield when isolated, you can really see the molecules in the vicinity of the nanoparticles, whereas the background is black, which means that the fluorescence is not high enough to be detected. And if you increase the distance, the separation, you can go to lower and lower contrasts. When you use the same size of nanoparticles with a silicon shell, but with no gold inside in the core, then you see nothing. If you make the same experiments with a highly fluorescent molecule, that's rhodamine, which has 40% of fluorescence, you see no contrast. You see the nanoparticles, but the contrast is not discernible. The values of the brightness are not so big as the ones predicted for molecules aligned with the radiation field. And this is a consequence of orientation average. Molecules are oriented randomly, and you get values that are intermediate between the maximum value and the value of 1. The second experiment I would like to show to you is an experiment we did in fixed cells that had internalized gold nanoparticles into actin filaments that were stained with Texas red phalloidine. The upper photographs A and B shows you a detail of filaments where nanoparticles are located. The lower time trace shows you two situations. One in black in the vicinity of a nanoparticle, and one with